I'd like to introduce Dr. Asmaa Boufridi from the University of Sunshine Coast, and she's going to tell us about her project concerning Manuka honey.
Thank you, Barry, and the Melbourne Beekeepers Club for inviting me today. I really appreciate the opportunity to tell you a little bit about what we do. So my name is Asmaa, and I'm leading the Honey Lab at the University of the Sunshine Coast. I took over after Peter Brooks, who probably many of you know, retired. I just would like to acknowledge the Gabi Kabi people who are the traditional custodians of the land where I am today, sharing this knowledge with you. We have a big collaboration with Hive Awareness that I would like to acknowledge, as well as Australian Manuka Honey Association. The Global Proficiency, the Honey Lab participates in this independent test verification. They send us honeys, we analyze it for the MGA content and various phenolics, which I'll be talking about today, and we get to report. The results that we get is also analyzed against many other labs. They analyze honey as well, so we can see if our methods are up to date or not. Global proficiency is about. For today's presentation, I'll be talking about the Manuka Honey Project, about what we do, how do we report our test, as well as the Leptosperin analysis. But I'd also like to tell you a little bit about the phenolic compounds profiling that we have been working on. Manuka Honey Project. Manuka honey is produced from the Leptospermum plant species in both Australia and New Zealand. Australia has predominantly one species of Leptospermum, which is the Scoparium, while Australia has over 80 species of Leptospermum. Not all those species are DHA and MGO active. At the Honey Lab, we test for these two specific Manuka markers, DHA and MGO, which is the active antimicrobial in Manuka honey, as well as HMF, which I'll be talking a little bit about later. HMF is not a Manuka marker, it's a honey age and heat treatment marker. From the MGO, we then calculate an estimated honey non-peroxide activity that we report as NPA. So usually beekeepers use this information for the labeling of their product, but also to monitor which sites are producing the best quality Manuka honey. It's important to note that in May 2023, Australia won the case brought by New Zealand interests. So New Zealand Intellectual Property Office recognized that Australia produces Manuka honey, and that Manuka is not restricted to only one species, which is really good for our industry. If you are interested in which species will give you high MGOs, there's this guide that it's free that you can download from AgriFuture, and it shows you the different species, where they can be found, how to distinguish them in terms of leaves and flowers. So this work has been done by Simon Williams in collaboration with Peter Brooks that we have here in the picture. MGO doesn't come from the plant. What comes from the plant is the DHA. So MGO is derived from DHA. So what we have here is our DHA that comes from the nectar. It gets transported by the bees in the nectar to hives, and then it gets converted as honey matures. So we found that young honey will have high DHA and low MGO levels. So what we do in the lab, we developed, before I started, the lab developed what we call a 3-in-1 reaction test. So we test for DHA, MGO, and HMF all at once. So because these compounds are a bit hard to see in our analysis, we tag them with another compound that we can see just here for us to be able to actually see them and quantify them to give us quantification of the concentration. So what we have is that DHA in nectar, it takes about a year to two to convert the DHA into MGO. That depends on how you store your honey, but also in terms of heat. So we recommend for people to not heat the Manuka honey because it's going to destroy the MGO in it. And we actually are able to see that. We can also analyze HMF in non-Manuka honey because it's not related to only Manuka. We have some beekeepers, they send us their honeys to analyze only for HMF to see an age and heat marker, if that honey is old or it has been heated or not. So we use the same technique. After we extract the honey, we analyze it by what we call a HPLC, which is high performance liquid chromatography. This technique allows us to actually separate those compounds in the big mixture of the honey. So what we have here is the sugars at the beginning. So we already extract most of the sugars during the extraction process before we analyze the honey. But we can still see here that we have a little bit of sugar left. By using the HPLC, this technique, we can actually get rid of it a little bit. And then what we see here is our DHA, which is found in the nectar. We have our HMF, our heat and age marker pointed here. And then we have our MgO at the end. So we can see our MgO is much more higher in this sample compared to DHA. Also your MgO, that's your antimicrobial compound. As mentioned earlier, young Manuka honey will have high DHA but low MgO. Once we analyze and quantify how much we have of those three compounds, we send the beekeepers a report. The report will have your name, it's protected, so no one has access to it. It gets sent only to you and will have the DHA, HMF, and MgO concentrations in ppm, as well as the non-peroxide activity, which is calculated based on the MgO levels. In collaboration with Hive and Wellness, we were able to map over 2 years so far, different areas where Manuka honey comes from and their levels of MgO or NPA in this case. So what we found is that most of the honeys we analyze at the Honey Lab, they come from New South Wales, followed by Queensland, and then Tasmania, and then Victoria, and then Western Australia and South Australia. But we also found that Southeast Queensland and Northern New South Wales, they have Manukas that are very high in MgO or MPA. In addition to measuring MgO, we also did what we call a honey activity estimator. We took different Manuka honeys and we store them at either 22 degrees, 37, and 65. And we wanted to see how the MgO is traveling through that heat. So we can show people that if you store your honey at 22 degrees, you are going to have the best conversion between your DHA and MgO. This is an example that shows us starting a DHA of 1,000 at 22 degrees. Between week 1 and week 52, you have that really nice conversion between DHA and MgO, reaching MgO of 326 after 52 weeks. But you also can see your HMF is quite low. So this is what it looks like. At 22 degrees, we have a slow increase over the 52 weeks. Your MgO is the orange dots that we can see. The blue is the DHA. So as the DHA is dropping slowly, MgO is increasing slowly. And then we have our HMF, which is the gray line that you see. It's quite stable. This compound, again, is a heat and age marker. So it's really nice. That's what we want to see. If we hit the honey at 37 degrees, what we see is that within 25 weeks only, we have our HMF, that heat and age marker, increasing. After 10 weeks, starting to increase, we can see DHA dropping quite quickly and our MgO increasing. And then after about 5 weeks, it starts to decrease. So we really don't want that. 65 degrees, that's like Peter Brooks would say, is turning your honey into Vegemite. So we can see in gray that your HMF, so within 8 weeks only, it's quite high. Your MgO start dropping quite quickly from the beginning. There's no increase at all. It's straight away start dropping. And your DHA is also dropping. So within 10 weeks, we're already quite low in MgO and DHA. So there's no more conversion between DHA and MgO anymore here. So that's an example of why we highly recommend for people, if they are working with Manuka honey and they have high DHA values of their Manuka, young Manuka honey, to actually leave it to mature at 22 degrees. We also developed what we call a blending calculator. That's for people when they have 2 different Manuka honeys and they want to blend them to reach a certain value of MgO. So before I start talking about that, we highly, highly recommend for people to never mix a non-Manuka honey with a Manuka honey. That destroys the MgO straight away. So the idea is to actually put the MGO of your first sample, what you are aiming for. So we recommend to people to use that extra 10% because, again, that's chemistry and things sometimes don't go as we want. And to enter the value in kilograms, the mass of the final honey that you want. So in this case, it's 200 kilos. So honey A, that's your first one, will have a 150 MGO value. Your honeybee will have 75 MGO value, and it tells you here how much of honey A and how much of honey B you need to mix to get 200 kilograms of Manuka honey at about 110 MGO. So we found that sometimes, very rarely, actually values a little bit down from what people are expecting, and that could be due to sometimes HMF that it's a bit high or probably heating. We recommend no heating during this blending. So this is what our regular day looks like in the lab in terms of analyzing Manuka honeys and MGO, DHA, and HMF levels. But we also have been working on Leptosperin. On the Yunfa website, they use Leptosperin as one of their markers to authenticate Manuka honey. Unfortunately, they hold the patent license for commercial leptospermum analysis by HPLC, and it's used for authenticating Manuka honey. Because of that patent, it prevents us in Australia labs to actually commercially test for leptosperin. So on their website, they define leptosperin as a compound found only in Manuka. So you can see the difference in pronunciation. So because the A has that little line, in New Zealand, they call it Manuka, while in Australia, we say Manuka. Manuka flower nectar and can only be created by nature. Measuring this unique compound ensures the authenticity of Manuka honey. Fortunately for us, patent license, they don't prevent us from doing research. So we developed fluorescence, which means glowing in the dark, analysis to measure leptosperin in Manuka honey. So the idea is by having leptosperin concentration, we can protect customers from adulteration and like fake honey and poor quality honey. A lot of people, they export honey, so they need that to indicate Manuka origin. It's also stable during storage. We also found that Manuka is not the full story. There are other compounds in Manuka honey that we can use. We published this paper late last year. Our aim was to isolate leptosperin. We isolated leptosperin from Australian Manuka honey. So we had the pure compound. Then we placed the pure compound in artificial honey. That was sugar syrup to just model the honey texture and analyze it by fluorescence response. What we have here is the calibration curve that we used. So the concentration of leptosperin that we prepared and also the response by fluorescence that we have here. And then we measured the fluorescence response of a range of Australian and New Zealand Manuka honey to show that actually leptosperin is in both. And to validate this method by fluorescence, we actually sent those same honeys to New Zealand for HPLC, leptosperin analysis. So earlier I told you we cannot use it for commercial testing in Australia because it has a patent, but it didn't prevent us from sending our honeys to New Zealand and actually get that value using the same method that they have it patent. So what we can see in this graph is that our leptosperin concentration by fluorescence that we developed in the lab was giving us exactly the same values, very, very similar, not exactly very similar as the leptosperin concentration analyzed by HPLC in New Zealand. So we were able to actually validate our method that it is working and we are able to analyze leptosperin by fluorescence. And because we published the result, it cannot be patented, which means people can actually use it. So we quantified leptosperin in the different Leptospermum species. In blue here we have Leptospermum scoparium, New Zealand. Orange Scoparium australian, we have Polygallifolium, Leversigii in the little yellow one, the light blue we have YTI, and the green one we have Spisosium. So what we found is that the 9 highest leptosperin levels were all from Australian honeys. But we also found that the maximum concentration of leptosperin in Australian Manuka was about 2,000 milligram per kilogram, while in New Zealand, Manuka was about 700 milligram per kilogram. So we have some species that have very high levels of leptosperin. So this is the end of the Manuka Honey Project. We have also been interested in phenolic compounds. So phenolics are those small molecules. If I can use this diagram to show you, when we have a flower, the plant produces small molecules. We call them phenolic compounds. So when the bees go and collect the nectar, they also collect those phenolic compounds in it. And then they take them to the hive, and then we actually find them in the honey later, those small molecules. Those phenolic compounds are known for their antioxidant, anti-inflammatory, neuroprotective, antimicrobial, cardioprotective, and anti-mutagenic properties. We're working on authenticating Australian honey, not only Manuka, but all Australian honeys, using these phenolic compounds and HPLC, the technique that I showed you before, high-performance liquid chromatography. We were able to develop a phenolic profile. So see it as kind of a fingerprint. So each honey from a specific plant will have specific phenolic compounds to it. We are trying to get a fingerprint of those phenolic compounds so we can link that honey to its floral origin. So not only this helps us protect the Australian honey industry from fraud, but also promote our consumers' confidence. So a lot of phenolic research has been done for European and Asian honey types. However, there has been little done on Australian honey. We started this project a couple of years ago. We published earlier in the year our phenolic profiles for various Australian monofloral honeys. What we call monofloral is a honey that has at least 50% coming from the same plant. So we know in Australia it's really hard because a lot of plants are actually flowering at the same time, but we are trying really hard to try to get as many monofloral honey so we can find those phenolic compounds specific to that plant. So we analyzed 7 species. So we had Maga ironbark, grey ironbark, brushbark, Ipuna, spotted gum, macadamia, and Coolibah. And what we have here is the number of samples or the honey coming from the same species. For example, Maga ironbark, we had 5 different samples coming from different regions or different people. So that was really good for us. So we were able, after 2 years, even though it's probably only one slide summarizing the whole thing, but we were able to find 49 out of 109 phenolic compounds that there were in these honeys, including 25 markers. What we call a marker is a compound that we can see in every single sample that we analyzed and tested. For example, if we had 4, let's say Maga ironbark, and a compound has been found in 3 of them, we're just calling it a phenolic identifier in that species. But if it's found in 4 of them, we are calling that a marker, because it has been consistent within those samples. Our in-house library of phenolic, we have about 109 phenolic compounds that we use to screen against all those honeys, and we were able to identify 25 of them. We took this project further and we applied it to Leatherwood honey. We were actually very fortunate to have a lot of samples of Leatherwood. So we had 32 samples from 2016 to 2023. So we had various years, but also various collection within the same year. So there was 4 samples for each extraction year. So we analyzed all of them individually, 32, but we went and combined actually the same year together. That was going to give us a representation of the standard Leatherwood within that year. We know that actually those phenolics, because they come from the nectar of plants, if there is a drought or it has been like a wet season, those phenolics can change sometimes. So we wanted to actually make sure that within that same year, we are having exactly the same markers. And we applied our library of 109 compounds. We were able to identify 20 phenolic compounds in all the samples, while we found that 14 were markers, which means that 14 compounds were found in every single leatherwood honey sample we analyzed. This is what a phenolic profile looks like using HPLC. So every single little peak that you see here, those little bumps, that's a phenolic compound. So you can see there are a lot. What we found is that this big one that has a number 5 on top of it was actually found in every single leatherwood honey sample we analyzed, either individually or the combined one. But it didn't match any of the compounds. We had 109 compounds. So we went on a search to find what this compound is, because it seemed to be a really important marker for leatherwood honey. So we used different techniques to identify it. One of them was a UV, comparing a UV, but as well as a mass spectrometry, which was able to give us the different atoms in that compound. And then we identify what that compound could be. We went and bought a standard, so that's a pure compound. We analyzed it at the same time as the honey, and we confirmed that it is a 4-methoxymandelic acid. It had exactly the same mass as the compound in the leatherwood honey, but also the same retention time and the same UV spectra. But we didn't stop there. We went ahead and analyzed the nectar of the leatherwood plant, and we were able to identify this compound in the nectar of the leatherwood. So it was definitely a marker for authentication of leatherwood honey. This project is actually ongoing. So again, phenolic compounds, but this time for Manuka honey. This is really brief. So we wanted to identify the different phenolic compounds in Manuka honey. MgO is widely recognized as the principal antibacterial, antimicrobial component in Manuka honey, but Manuka does also display antioxidant, anti-inflammatory effect, as well as being linked to anti-cancer benefits. MgO is actually deactivated in the gut. Those properties are unlikely linked to MgO. So we tested those phenolics because we know they have a lot of properties, and we have seen that Manuka has a very unique phenolic and aromatic component that are more likely responsible on these health benefits. We also found that actually Manuka has 10 to 20 times more phenolic compounds than other honeys. And here we have an example of Australian Scoparium, New Zealand Scoparium. So all these peaks that they are highlighted with numbers, they are phenolic compounds. We have Liversa GI, Polygal, YTI, and Spisosium. But when we compare all of them to macadamia at the very bottom, we can see that they have much more higher phenolic compounds concentration than in a non-Manuka honey. This is still a work in progress at the moment. This is the team doing our consultancy, so analyzing for MgO, DHA, HMF, but also running research in parallel. So we have Peter Brooks, Georgia Moore, myself, and Chao Tran. If you have any questions, please feel free to email us or give us a call. Thank you.
It's lovely to see the research that you've been involved with, and we wish you good luck for your endeavours in the future. Thank you very much.
Thank you so much, Barry. I really appreciate it. Thank you.